Question 4. A voltimeter is connected in parallel with a variable resistance, capital R, which is in series with an ammeter and a cell. The cell of EMF, capital E, and internal resistance, small r, for one value, capital R1 of variable resistance. The ammeter reads 0.3 amps and the voltmeter reads 0.9 volts. For another value, R2 of the variable resistance, the ammeter reads 0.25 amps and the voltmeter reads 1.0 volts. Neglecting the resistance of the meter, find the value of R1, R2, E, capital E, and the small r. Solution. From the equation, capital E minus capital I times small r equals to capital V. Substituting the values, we have that capital E minus 0.3 for the I times R is equals to 0.9 for the V, which is our equation 1. For the second circuit, we have capital E minus 0.25 times small r, which is equals to 1.0 for the capital V, which is our equation 2. Making capital E the subject of the formula for equation 1 and 2, we have for equation 1 it will become E is equals to 0.3R plus 0.9. This will be our equation 3. Then for equation 2, capital E is equals to 0.25 times small r plus 10. This will be our equation 4. Since the E's are the same, equating both equation 3 and 4, since they have the same electromagnetic force, we now have 0.3R plus 0.9 is equals to 0.25 times small r plus 1.0. Then collecting like terms together, we have that 0.3R minus 0.25R is equals to 1.0 minus 0.9. Then which we now have 0.05 times small r is equals to 0.1. Then making r the subject of the formula, we now have 0.1 all over 0.05, which will now give us 2 ohms. From our equation 1, capital E, the electromotive force, minus 0.3R is equals to 0.9. Since R, we have gotten our R to be 2 ohms, we now substitute the value to have capital E minus 0.6 equals to 0.9 from capital E minus 0.3 times 2 equals to 0.9. Then for the resistance, R1 is equals to capital V1 over I1, which is equals to 0.9 over 0.3, which will give us 3 ohms. R2 is equals to capital V2 over I2, which is equals to 1.0 over 0.25, which will give us 4 ohms. Electrical energy and power. Electrical energy. The work done, capital W, or energy released in 1 joule when 1 coulomb moves between a potential difference of 1 volt. Energy is equals to capital W equals to capital Q times capital V joules, which is also equal to capital IVT joules, which is equal to capital V squared T all over R squared, or which equals to I squared R T joules. Example 1. A heater coil is required to give 420 joules every 7 minutes when working for a 2-volt supply. When the length of 32 SWG Eureka wire is required to make the coil, if the wire has a resistance of 0.8 ohms per minute. Solution: let R be resistance of the heater coil. Heat to be generated by the heater coil, V squared T all over R is equals to 2 squared times 7 times 60 to convert 7 minutes to seconds all over R. But the energy is 420, which is equals to 2 squared times 7 times 60 all over R, making R the subject of the formula. We now have R, capital R, is equals to 2 squared times 7 times 60 all over 420. Length of Eureka wire required is equals to 4 over 8, which is equals to 0.5 meters. Example 2. A potential difference of 6 volts is used to produce a current of 5 amp for 200 seconds through a heating coil. Calculate the heat produced. Solution: heat produced is equals to IVT, which is equals to 5 times 6 times 200 joules, which gives us 6,000 joules. Example 3. Looking at figure 4.7 example, calculate the total heat energy developed in 5 minutes by the system above. Solution: the effective resistance R is parallel is given by 1 over R is equals to 1 over 40 plus 1 over 40, which is equals to 1 plus 1 all over 40 to give us 2 over 40. Therefore, R is equals to 40 over 2, which is equals to 20 ohms. The total energy developed is equals to I squared ROT, which is equals to 1.2 squared times 20 times 5 times 60, which will give us 8,640 joules. Electrical power. Electrical power, P, is defined as the energy liberated per seconds in a device. From the above definition, we can express power in any of these three forms. Capital P is equals to VI, which is equals to V squared over R, which is equals to I squared capital R, which is in watts. The unit of electric power is watt, capital W. The larger unit is the kilowatt, kW. 1 kilowatt equals to 10 raised to power 3 watts. Example 4. Looking at figure 4.18, calculate the total power drawn from the cell in the circuit diagram above. Solution: combine resistance in parallel. Capital R is equals to 4 times 4 all over 4 plus 4, which gives us 16 over 8, which is 2 ohms. Combine resistance in parallel is equals to capital R equals to 4 plus 2, which gives us 6 ohms. Therefore, the total power drawn from the cell is equals to V squared over R, which equals to 12 squared over 6, which equals to 144 over 6, which equals to 24 watts.